Hello my friends and welcome back to the You Can Do TV channel.
The strength of construction often begins long before concrete is poured. Rodbusters step onto the rebar grid, carrying wire, hooks, and determination. The process starts with laying out steel bars, aligned in a lattice to shape the foundation's skeleton. Workers then bend and position crossbars, ensuring stability for the structure. Tying wire is the defining task, each joint wrapped tightly with swift, practiced motions. The rhythm builds as thousands of ties secure the grid. The speed is impressive, but the endurance is even greater. Their teamwork transforms loose bars into a rigid frame. It's inspiring to see strength formed by unity. The scale of bridge building commands admiration, and the incremental launching method is one of its most striking techniques. On the Kuzi Marmara Highway, engineers apply this system to advance massive deck segments step by step, shaping viaducts that stretch across difficult terrain. The sight of steel and concrete moving as one is unforgettable. The sequence begins at the casting yard, located behind an abutment. Here, inner formwork is closed, creating the mold for the first segment. Concrete is poured, about 280 cubic meters in the early stages, solidifying into the foundation of the deck. Every pour carries anticipation, for strength is being born. Once hardened, the formwork is opened and shifted. Workers install upper formwork, withdraw the inner mold, and mount reinforcement and ducts. Around 65 tons of steel reinforcement and post-tensioning sheath are set in place, anchoring durability into each segment. The effort of lifting and positioning every bar is immense. Next, nearly 480 cubic meters of concrete is poured into the extended deck. After curing, steel tendons are threaded through ducts in preparation for stressing. This step demands synchronized effort, reflecting the unity of the team. Post-tensioning then compresses the structure, locking strength into the concrete. Launching follows. Hydraulic jacks push the finished segment forward about 5 meters per hour, sliding it across temporary supports. In 10 hours, 55 meters advance. In 8 days, the bridge spans grow steadily. The steady push forward captures the determination behind the project. Segment after segment, the viaduct extends over valleys and obstacles, uniting engineering design with practical execution. The balance of force and control is extraordinary. What begins as steel and formwork transforms into a continuous pathway. The dedication poured into the process deserves deep respect. Innovation takes shape on the track in Clermont-Ferrand, where used tires find a new life as a full athletic surface. Aliapur and Technisol work together to design a system that transforms waste into performance. The idea of athletes running on ground made from tires is striking, both technically and environmentally. The journey starts with 9,000 worn tires. They are shredded into smaller pieces, separating steel and textile from the rubber. This process yields calibrated granules between 1 and 4 millimeters. 40 tons of this material were required to cover the 800 square meters of track. It's fascinating to see how something discarded is refined into material with exact properties. Before laying the new surface, the old coating is removed, A bituminous layer is spread to improve adhesion. The rubber granules are then blended with a polymer binder to create a uniform mix. Spread across the base, this layer forms a resilient foundation 16 millimeters thick. A finishing machine smooths the surface, while manual troweling ensures seamless joints. The combination of machinery and human touch adds remarkable harmony. Once dry, the track is marked. Specialized paint and precise surveying guarantee compliance with athletic standards. The final surface not only meets durability needs, but also provides rebound and shock absorption. Knowing that over 50% of the material is high-quality elastomer inspires confidence in every stride. Massive equipment movements showcase the scale of maritime engineering in the Middle East. At the Boskalis Technical Center in Ras Al Khaimah, teams coordinated a loading operation of 200 metric tons onto the barge Giant 6, bound for Duqm, Oman. The size of the cargo alone leaves a lasting impression. The process began with receiving pontoons, cutter heads, anchors, coupling towers, and floating hoses shipped from China, South Korea, Sweden, and the USA. Each pontoon weighed 30 to 35 tons, cutter heads 25.7 tons, anchors 30 tons, and coupling towers 38 tons. Every number highlights the intensity of the task. Local fabrication partners contributed 2 bow coupling towers, designed by Boskalis and certified for quality. It is striking how international supply lines converge at one site. 47 floating hoses, each 14 to 20 tons, were staged for loading. The logistics flow feels like a puzzle solved in motion. The barge Giant 6 was submerged to load vessel BKM 104, supported by tugboats BKS 292 and Guayas. After securing, the Union Diamond anchor handler towed the barge toward Oman. Moments like these emphasize human coordination with immense machines. Customs, immigration, and port clearances were handled internally. The achievement stands as a milestone in complex maritime mobilization. Construction evolves when materials are matched with smarter techniques, and vertical AAC panels represent that evolution. Vertical AAC wall panels present a modern approach, offering an alternative to traditional bricklaying while maintaining structural reliability. This method highlights how construction sites benefit from both speed and durability. The process begins with panels that arrive reinforced for transport, ensuring they can be lifted and positioned securely. Installation crews handle these elements with cranes or hoists, guiding them into place along the building frame. It is remarkable to observe how such large components align so seamlessly. Panels are designed with grooves and tongues that interlock, allowing walls to stand firm without excessive mortar. This connection system also improves insulation and stability in residential housing projects. Next, workers apply adhesive mortar at the joints. This step binds the vertical elements while keeping wall thickness uniform. The rhythm of each panel being set one after another builds a clear sense of progress. Compared to laying bricks individually, the method saves both labor and time. Builders gain the advantage of creating straight, stable surfaces quickly, ready for finishing. There's a satisfying efficiency in watching walls rise evenly within hours instead of days. Once the panels are in place, final adjustments ensure proper alignment. Openings for doors and windows are accommodated during placement, reducing the need for later modifications. It is impressive how much thought has gone into minimizing rework on site. With panels secured, Surfaces can then be prepared for plastering or direct finishes. The outcome is a wall system that combines modern production with practical application. This approach shows how building technology continues to evolve while remaining grounded in everyday construction needs. Hummin. At the edge of Lima, the port of Callao rises as the most vital hub of the Pacific. Decades after its original construction, the terminal had reached its limits. Modernization was no longer an option but a necessity. The transformation that followed reveals both scale and ambition. The project focused first on rebuilding Pier 11 and Pier 5. Pier 11 now stretches 280 meters, dedicated to bulk and general cargo, while Pier 5 extends 560 meters, tailored for containers. Each pier rests on driven steel piles, topped with prefabricated beams. Seeing massive piers take shape over the water conveys a rare sense of progress. Demolition came before growth. Old pavements and buildings were cleared, making way for a 5-story administration facility with rooftop access, a 2-floor public building, and new maintenance areas. The container yard expanded to 157,000 square meters, ready to support far more activity. The scale of cleared space alone feels immense. Engineering challenges demanded creative solutions. Cofferdams were deployed to create dry enclosures for cutting, welding, and preparing pile caps beneath sea level. These supports allowed prefabricated beams to settle securely above. The ingenuity behind working underwater is striking. Infrastructure improvements extended to power distribution. 600 outlets were installed for refrigerated containers, stacked up to 5 levels. The port's capacity jumped from 900,000 to over 1.2 million TEUs. Numbers like these show how infrastructure can reshape logistics. New technology redefined cargo handling. OCR systems at the terminal entrance read truck and load data automatically. 4 Super Post Panamax STS cranes and 12 electric RTG yard cranes joined operations. The sight of such equipment signals a new era in port handling. Beneath Pier 11, underground conveyors and grain hoppers enabled direct truck loading or silo transfer. Efficiency rose further with mobile cranes and 3 mega hoppers. Throughout, more than 600 workers contributed, with 95% hired locally. Their labor and expertise ensured that modernization advanced while the port stayed operational. Behind every figure stands the dedication of people shaping the future of trade. Spanning the Senku River at Mount Marusi in Lesotho. This bridge project highlights the combination of steel and concrete in modern infrastructure. Measuring 142 meters in length and 11 meters in width, the structure relies on 2 abutments and 3 piers to carry road traffic safely across the river. The scale of construction instantly conveys a sense of determination and vision. The foundation work begins with excavation and preparation of the riverbanks. Concrete abutments are poured and reinforced to anchor the future deck. Massive formwork and scaffolding allow crews to shape the supports with accuracy. Each movement of material seems to carry the weight of progress forward. With the abutments set, the 3 piers rise from the riverbed, stabilized by cofferdams and reinforced steel cages. Their alignment is critical for supporting the steel superstructure. The balance between natural forces and human engineering becomes very clear at this stage. Steel girders are then assembled and lifted into position. Heavy lift cranes align each segment, forming the composite frame of the bridge. Concrete decking follows, tying the steel skeleton into a single roadway. The joining of steel and concrete feels both powerful and enduring. Final surfacing and safety installations complete the bridge. The result not only connects communities, but also reflects Lesotho's growing capacity for major engineering achievements. The finished view inspires confidence in infrastructure that will serve generations. Aerated concrete block construction depends on discipline, and the thin bed mortar method secures strong bonds with time-saving advantages. Yatong blocks, with tongue and groove joints and tight dimensional tolerance, allow quick handling and clean masonry. The way each element aligns brings a quiet sense of satisfaction. The process begins with preparation. Tools include a bucket, trowel, spirit level, saw, planer, rubber hammer, string line, and mortar mixer. A bitumen sheet is laid as a damp-proof layer. Normal mortar is mixed and applied so the first corner block can be seated firmly. With hammer and level, workers bring it into exact height and position. Watching the cornerstone fixed in place feels like the foundation of trust. Once aligned, a string guides the next blocks. Thin bed mortar is mixed with precise water ratio, rested for 5 minutes, then stirred again. A 1 to 2 mm mortar layer is spread, ensuring narrow joints. The thinness of the layer highlights how accuracy matters more than bulk. At corners, vertical joints are filled for stronger bonding. Cutting follows where needed. Blocks are marked and sawn with hand or bandsaw. Extra grooves may be trimmed to ease bonding. For the second course, another damp-proof coat may be applied using sealing slurry. Stones are wetted, brushed twice, and cured before placement. The new layer starts again from the corner, keeping a 0.4 height overlap rule. String lines ensure openings like windows stay true. As rows rise, reinforcement strips are set between blocks to distribute loads. Uneven surfaces are leveled with a planer. At required height, lintels are placed into prepared recesses, bonded in both horizontal and vertical joints. Seeing the lintel locked in feels like a milestone. The wall's top edge is ground smooth to avoid chipping when slabs are added. Exposed masonry crowns are covered with foil to prevent moisture during rain. Small defects are repaired with filler. The final result shows order, endurance, and pride in skilled work. Each stage, though simple, carries the weight of craft. Granite blocks arrive at the facility as enormous rough masses, waiting to be transformed into usable stone. Workers use saws to square edges and remove irregularities. This step ensures the slabs will have clean lines and uniform dimensions once they are produced. The accuracy of this preparation sets the tone for everything that follows. Surface processing then begins, where polishing heads fitted with abrasive pads grind layer by layer. The effect is gradual yet striking, as texture softens and natural colors brighten. This treatment not only enhances the visual appeal, but also boosts durability. Before these refinements, the granite had already undergone its defining transformation. Large gang saws, equipped with dozens of steel blades, sliced the massive blocks into slabs. Their motion, combined with water and abrasive material, cut through dense stone with relentless force. Final inspection confirms thickness, flatness, and gloss, ensuring every slab meets standards for construction or decoration. Smart design meets practical results in the double book mold system shaping sandwich panels. The concept fascinates immediately, as two different molding surfaces combine to create one highly functional panel. Phase 1 begins with preparation. The mold surfaces are cleaned, and release agent is applied. Side shutters are set using hydraulic and mechanical extensions to match the required width. Window molds are fixed by magnets, while reinforcement steel is placed on surface A. Concrete is then poured and vibrated briefly to settle. At this stage, insulation is added and secured, with thermopins penetrating several centimeters into the concrete. These pins will later bond both panel halves together. While surface A cures for about 7 hours, workers simultaneously prepare surface B by repeating the cleaning and shutter setup. Phase 2 starts when surface A reaches initial strength. The hydraulic system tilts the panel vertically. Locking pins and bars hold it in place, and magnets for window molds are released. Now surface B is filled with concrete, embedding the thermopins into its mass. The curing process continues for another 9 hours, gradually consolidating the structure. The tilt and cast method shows a smart balance between stability and efficiency. Phase 3 concludes the cycle. Once surface B achieves a strength of around 14 to 15 megapascals, the completed sandwich panel is released. Hydraulic systems disengage the shutters, the mold returns to horizontal, and an overhead crane lifts the panel out. Final placement into storage marks the end of an approximately 19-hour cycle. Watching such a structured process sparks admiration. Massive panels emerge with smooth finishes, ready for installation, requiring minimal post-processing. This approach combines engineering practicality with reliable construction results.
A powerful surge of engineering determination opens the scene, revealing reinforced concrete giving way under robust machinery. The KEM ROC DMW 220 cutter wheel, mounted on a CAT 349 EL excavator, begins cutting into reinforced bridge concrete with focused force. First, the raw concrete slab is grooved deeply, weakening its mass. Then the cutter slices through thick, stubborn rebar and concrete, breaking the structure into 6 to 10 ton segments. Those heavy pieces are lifted away for disposal. It's awe-inspiring how sinewy steel and dense concrete yield to mechanical resolve. The result is a clean, efficient demolition, balancing strength with movement in perfect harmony. Mountains of cargo press down on trucks built for far less, turning every journey into a gamble with gravity. In this compilation, the original sounds of Chinese trucks pushed far beyond safe limits deliver an audio assault that commands attention. The first moment captures a truck's engine, revving under strain, gravel rattling beneath its weight. Load estimates suggest some trucks exceed rated capacity by more than double, severely stressing axles and suspension. Drivers feather the throttle to balance torque, preventing sudden stalls on uneven terrain. It's staggering how sound reveals what overload cannot hide. Next, recordings shift to multiple trucks idling side by side, their motors chugging unevenly with exhaust rasping. Uneven exhaust pressure indicates partial combustion, often linked to clogged injectors when engines are overworked. Operators often downshift aggressively, allowing momentum to carry them through brief uphill sections. The contrast between engines offers a raw diagnostic insight no visuals can match. Some trucks maintain higher RPMs intentionally, sacrificing fuel economy to avoid engine knock. Then the clip moves to trucks climbing inclines under load, their engines roaring in laborious harmony. Torque readings in similar cases show gear teeth wear increases rapidly under such overload. Each rev trembles with the tension of too much weight clashing with machine limits. Others hug the road edge to find firmer ground, reducing slippage on steep grades. Finally, the compilation ends with trucks throttling on flat surfaces, their engines trailing off into distant rumble as if gasping for relief. On long stretches, drivers pulse the accelerator, instead of holding it steady, easing constant stress on the drivetrain. One can't ignore the voice of the machinery crying out. Even as components strain, trucks lurch forward in small bursts, clawing distance with every struggling gear change. Through these sound bites, a narrative of overload, endurance, and risk emerges purely through audio. It's both unnerving and enlightening how much detail hides in engine cries. The persistence of these machines under punishing loads speaks to both human determination and raw mechanical resilience. Mombasa, Kenya's coastal hub, stands at the core of East Africa's transport network. The port receives massive cargo flows, and roads must absorb that pressure. To respond, the Kenya National Highways Authority initiated a portfolio of highway upgrades designed to relieve congestion and expand access. The first step was the Mombasa Port Area Development Project. Engineers constructed a dual carriageway linking Miritini to the new Kipavu container terminal. 2 interchanges and an access road to Moi International Airport were added, cutting delays between port and airport. Next, the Port Rights Airport access road was widened to a 4-lane dual carriageway with grade-separated intersections. This design eliminated conflict points and allowed heavy trucks to flow without disrupting cross-traffic. Further north, The Nairobi-Mombasa highway upgrade strengthened bituminous layers and expanded sections into 6 lanes. Street lighting, footpaths, and service roads improved safety. Ongoing phases include the Dongo Kundu bypass, with bridges over tidal inlets. Locals watching construction describe relief that traffic chaos is finally easing. Each completed link feels like a long-awaited breakthrough. A cruise ship offers a spectacular sight of engineering at its grandest scale. The Aida Prima, a Hyperion-class vessel, was built by Mitsubishi Heavy Industries for Aida cruises. Stretching 300 meters in length, 37.6 meters in width, and weighing 124,500 gross tons, it embodies the ambition to merge travel comfort with advanced technology. Each stage reveals not just size, but the ingenuity required to put thousands of parts into a single floating city. The construction began with keel laying, where massive steel blocks were assembled to form the base. Heavy cranes lifted prefabricated sections, setting them precisely into place on the slipway. Over time, dozens of these blocks fused into a continuous hull, stretching the full 300 meters. It is impressive to see how coordinated teamwork allows such heavy sections to align seamlessly. Welding crews connected the plates while inspection teams ensured every seam was secure. Next came superstructure assembly. Deck by deck, modules were lifted onto the hull, creating the multi-level skeleton of the vessel. Cabins, corridors, and service areas were gradually added, turning steel into habitable space. The 643 staterooms were designed in 14 categories, ranging from compact rooms to expansive suites with walk-in closets, private verandas, and open sundecks. The scale of interior outfitting alone feels like equipping a luxury hotel several times over. As construction advanced, Mitsubishi applied its Mitsubishi Air Lubrication System, MALS. This innovative feature forms a layer of small air bubbles along the underside of the hull, reducing friction with seawater and improving fuel efficiency by around 7%. The ship was also fitted with advanced exhaust gas treatment systems, filtering harmful emissions such as soot, nitrogen oxides, and sulfur oxides. These environmental measures show how new vessels aim to balance performance with sustainability. Attention then turned to outfitting. Electricians, plumbers, and HVAC teams moved inside, weaving miles of wiring, piping, and ventilation ducts. Furniture, lighting, and decorative finishes gave each room its identity. Lanai staterooms on Deck 8 introduced winter gardens with foldable glass walls, while panorama rooms connected directly to a private patio deck. It is remarkable how these living spaces offer both privacy and a sense of openness at sea. The upper decks included entertainment and leisure facilities, restaurants, bars, swimming pools, and landscaped areas. Shipbuilders integrated complex water features and a protected patio deck for guests. The 32 suites, offering up to 82 square meters of private sundeck, set a standard of luxury rarely matched in cruise construction. Every detail, from the placement of windows to the flow of hallways, shapes the passenger experience. Final stages included painting, launching, and sea trials. Workers coated the exterior in Aida's distinctive design before the vessel touched water for the first time. Sea trials tested propulsion, maneuverability, and safety systems under real conditions. Adjustments ensured that the vessel could operate safely on its future global routes. The moment a massive ship leaves dry dock carries both relief and pride for the builders. The Aida Prima emerged as a new generation cruise liner, built not only for comfort but also for efficiency and environmental responsibility. Filmed through years of dedicated time-lapse photography by MK Timelapse, this project captures the transformation of raw steel into a traveling city. For those who love engineering, the result is as breathtaking as the journeys the ship will one day host. At a massive scale of construction, size itself becomes the defining challenge. The Westerend project showcases the placement of the longest prestressed concrete girders in the Netherlands, each measuring an impressive 61.75 meters. These giant beams would form the backbone of the new bridge across the Ringvaart, demanding precise handling and seamless coordination. The first phase commenced as the girders were transported from the Rasdorp junction. Instead of following standard roads, the transport convoy moved backward through farmland along a specially built 3-kilometer work road. This unusual method minimized disruption and allowed direct access to the construction zone. The slow, deliberate journey across fields felt like guiding a massive creature. Once delivered, the girders were positioned onto pontoons floating in the Ringvaart. The calm water served as a temporary staging area, where beams rested before final lifting. Crews monitored stability constantly, ensuring no shift during waiting. Seeing such weight supported on water adds a dramatic tension. The final stage involved two 700-ton cranes operating in tandem to lift each girder into place. Over 3 days, 25 beams were carefully installed across the span. The scale of machinery mirrored the scale of the girders themselves. Each placement carried a mix of suspense and relief. Every move of the crane seemed like a test of strength. At a remote African site, engineers handle a 450 kilowatts Francis turbine with care and expertise. Components are lifted, aligned, and secured within the powerhouse. The team's coordination ensures reliable power generation for local facilities. The magnitude of each assembly impresses deeply. Golden wheat arrives in large trucks, ready for processing. At the unloading pit, the worker positions himself beside the truck's release handle. He begins rotating the crank, the mechanism gradually sliding open the gate. Each turn adds tension, as if unlocking stored energy. Soon, a stream of wheat pours through the opening, striking the grate below. The steady flow creates a sound that seems almost endless. The worker continues turning, widening the outlet for faster discharge. Effort in his motion mirrors the force of the grain. Below, conveyors wait to capture the falling crop, sending it deeper into the system. This moment closes the journey from truck to bin. At Ansta Bildemontering AB, end-of-life vehicles face a powerful transformation. A Volkswagen Jetta is positioned carefully within the crushing chamber, ready for compression. It's striking to see a full car reduced to a compact block in moments. Hydraulic presses apply immense force, folding metal with mechanical authority. Panels, frames, and internal structures collapse, layer by layer, into a dense, manageable shape. Workers monitor gauges and controls, ensuring the press operates safely and efficiently. The energy and force involved make it clear how much engineering is needed behind such a simple action. Once fully compressed, the car is removed and prepared for recycling, ready to re-enter the material stream. Every stage highlights both industrial power and systematic control, turning a retired vehicle into raw material for future use. Transporting massive transformers requires ingenuity and exact planning. At Smith Transformers in Nijmegen, 3 heavy transformers were prepared for their final journey. The challenge lay in crossing the A12 highway and an elevated train track running parallel to it. Standard ramps would have demanded long highway closures, creating logistical complications. Engineers devised an innovative solution. The transformer transporter itself was placed atop a secondary vehicle, forming a 2-layer system to overcome the height difference instantly. Hydraulic jacks on the lower vehicle were calibrated to maintain perfect balance under dynamic loads. It is impressive to see such large equipment moved with careful coordination and engineering insight. Steel plates were strategically positioned over the train track to support the weight of the upper transporter. The highway was closed briefly, and the top transformer smoothly rolled onto the bridge, while the underlying vehicle supported its weight. Load sensors monitored pressure distribution continuously, ensuring no structural overstress occurred on the bridge. Once cleared, traffic resumed except for the right lane, demonstrating efficient control of public infrastructure during heavy industrial operations. The team maintained constant communication, ensuring each movement was timed perfectly. The vehicle's suspension system was adjusted in real time to accommodate minor surface irregularities, maintaining transformer stability. Watching the interplay of vehicles, cranes, and human coordination evokes a real appreciation for problem-solving under constraints. As each transformer crossed, the empty lower vehicle returned immediately, allowing the next transformer to proceed without delay. Precision alignment markers guided the top transporter onto the bridge, reducing the risk of lateral shifts. The final unit waited until sunrise, enabling an aerial camera to capture the operation for documentation and verification. Each moment highlighted the scale, weight, and precision involved, showing the transformative impact of clever engineering. Torque-controlled winches assisted in gradual positioning adjustments, preventing sudden load shifts. By the end, all 3 transformers were positioned safely on the rail bridge, ready to continue their transport route. The operation not only illustrates the complexity of moving extremely heavy industrial components, but also the ingenuity of logistics and planning. It's remarkable how strategic thinking, engineering calculations, and careful coordination combine to move objects of such magnitude safely. Every participant, from engineers to drivers, contributes to the seamless execution of this large-scale transport, emphasizing teamwork, timing, and safety in every step. GTREX amphibious excavators demonstrate engineering design for challenging water and swamp conditions. The process involves assembling the Texas Series undercarriage, which supports 8-ton, 14-ton, and 20-ton excavators. Each undercarriage undergoes hydraulic testing to ensure stability during extended operations. The long arm is mounted carefully, allowing compatibility with multiple excavator brands. Operators check the boom articulation under load to confirm smooth movement and reliability. Side pontoons are attached to enhance buoyancy, creating a stable floating platform capable of supporting heavy excavation work. Spud piles are installed next, providing additional anchoring and control in soft soils. Once assembly is complete, the excavator is tested on shallow water to verify flotation and maneuverability. All hydraulic connections and joints are pressure checked for leaks, guaranteeing operational safety. The combination of human expertise and mechanical design ensures these amphibious machines can perform in environments that challenge conventional excavators. Engine performance and hydraulic flow rates are calibrated to optimize digging efficiency. Watching these machines glide across wetlands and lakes is impressive, showing how engineering adapts to nature's obstacles. The GTREX system highlights versatility, strength, and reliability in each unit, ready to tackle complex aquatic projects. The sight of the silver spade dominates the horizon, its immense size, a reminder of the engineering power behind surface mining. On this occasion, however, the focus is not on digging coal, but on preparing its path. The task at hand involves placing 18-inch mats beneath the crawler tracks, ensuring that the ground can support the extraordinary weight of this machine. The scale of preparation shows just how demanding it is to move such a giant. These mats, 18 inches thick, are constructed to endure the crushing loads of thousands of tons. Bulldozers and support vehicles work in unison to unload them at the designated areas. It is remarkable to see how even the mats themselves look oversized, yet they appear small compared to the shovel. The ground crew positions the mats close to where they will be laid, creating a stockpile for continuous placement. Once unloaded, the mats must be shifted into the right alignment. Instead of relying solely on support vehicles, the bucket of the silver spade is employed to manipulate mats directly. Operators skillfully adjust their movements to line the mats in front of the shovel's tracks. The coordination between human control and mechanical force is impressive, revealing the teamwork required in this task. With every adjustment, the path for the shovel gradually takes shape. Suspended by its massive cables, the bucket lowers to grip or push mats into exact positions. The size of the bucket allows it to move several mats at once, saving time and reducing reliance on smaller machines. Seeing a bucket designed for scooping earth handle mats with precision is both unexpected and fascinating. This dual-purpose use of the bucket showcases the adaptability of mining equipment when faced with logistical challenges. With mats roughly in place, ground workers step in to perform fine adjustments. Wearing helmets and safety gear, they guide the mats into straight lines under the crawler's future path. There is a sense of tension as workers move close to the massive shovel, highlighting the balance between risk and control. The accuracy here is essential, since any misalignment could compromise stability. As mats are secured, the shovel begins to advance. Each forward movement covers several mats, pressing them into the soil and creating a reinforced surface. The procedure repeats as new mats are pulled from the stockpile and shifted ahead of the shovel. Watching the shovel slowly crawl forward while mats are continuously set ahead gives a sense of unstoppable progress. The movement may seem slow, but it is steady. The final stage involves repeating this cycle until the shovel reaches its intended position. Mats are transported, shifted, positioned, and aligned over and over. The repetition underlines the sheer persistence needed to move machinery of this size. As daylight shifts, the operation maintains its rhythm, with trucks, loaders, ground crews, and the shovel all working as one. The placement of 18-inch mats may look like a supporting task, but it is fundamental to the operation of the silver spade. Without this preparation, the machine could not move safely across unstable ground. It is awe-inspiring to realize how much planning and effort goes into every step of relocating such a giant. What appears simple, laying mats, is actually a demonstration of coordination, strength, and foresight. By the time the shovel advances fully, hundreds of tons of mats have been set, creating a foundation strong enough to carry one of the largest earth-moving machines ever built. Energy progress in Brazil takes shape at Sobradinho, where modernization renews a hydro plant first opened in 1979. Work begins with the refurbishment of 6 generating units, each linked to vertical Kaplan turbines that have been in service for more than 4 decades. Engineers upgrade worn components, restoring efficiency and ensuring stable operation. Continuous monitoring ensures optimal performance, and the renewed units are tested for efficiency, restoring the plant's capacity of 105 OMW. The transformation safeguards reliable power for over 1 million homes. Power takes shape through gears that are born to handle relentless industrial demands. The process begins with forging and machining large steel blanks, shaping them into durable gears and shafts. Heat treatment follows, strengthening the metal for extreme industrial loads. In parallel, specialized machines cut gear teeth with exact geometry, ensuring smooth torque transfer. Assembly unites shafts, bearings, and housings into complete gearboxes, each tailored for industries like mining or steel. Rigorous testing under load verifies performance and durability before delivery. The atmosphere inside the facility highlights both scale and purpose. Each stage feels like progress toward unstoppable mechanical power. Precision and engineering ambition dominate the workshop as Lagoon Gemini's lathes demonstrate their multi-process capabilities. Each machine is designed to perform turning, milling, drilling, and grinding, integrating functions that traditional lathes handle separately. The sight of raw metal being shaped sparks admiration for human ingenuity. Even at the setup stage, the attention to alignment and calibration is remarkable, hinting at the complexity to come. The process starts with setting up the lathe, securing the workpiece in the chuck, and calibrating the machine for multiple operations. Operators align tools for turning first, cutting cylindrical shapes from solid steel or aluminum billets. Every rotation seems to reveal hidden potential in the raw material. Coolant flows steadily during cutting, keeping temperatures controlled and maintaining material integrity. Next comes milling. The lathe transitions smoothly between operations, using programmed coordinates to create slots or grooves in precise positions. Milling heads rotate at controlled speeds, allowing for high feed rates without sacrificing surface finish. Operators carefully monitor cutting forces to prevent tool deflection during deep cuts. Specialized clamping ensures the workpiece remains stable even under complex milling operations. Tool paths are verified digitally before engagement, reducing error and increasing efficiency. High-precision end mills with multiple flutes are selected based on material hardness for optimal chip removal. Dynamic compensation adjusts for thermal expansion during prolonged milling cycles. Adjustments to spindle speed and feed rates optimize cutting efficiency for each material type. The machine's flexibility reduces handling time while maintaining exact tolerances. Tool changes are managed efficiently, allowing quick swaps without breaking workflow. Throughout production, operators monitor temperature, vibration, and cutting forces, adjusting feeds and speeds as needed. Safety measures are strictly followed, ensuring both machine and operator are protected. The combination of technology and human oversight highlights the depth of expertise required. Periodic checks ensure that tolerances remain within strict specifications. Grinding is the following stage, where surface finishing is enhanced. The lathe's grinding attachments polish metal to achieve high-quality smoothness and geometric consistency. It is impressive to see how one machine accomplishes what once required multiple setups. Operators use digital readouts to confirm finishing depth and alignment. Lagoon Gemini's lathes exemplify how engineering vision becomes tangible through integrated manufacturing solutions. Quality documentation is maintained for each part, ensuring traceability and accountability. Expert handling and responsiveness define premium metal panels, and the P4-2116 delivers both in every operation. The combination of heavy gauge handling and automated adjustments highlights the skill embedded in modern manufacturing. The process starts with loading sheet metal blanks onto the machine. Each piece is positioned according to kit specifications. The ABA automatic blank holder ensures each blank is secured with consistent pressure. Observing the machine adjust itself according to material differences shows how engineering bridges human oversight with automated precision. Mach 2.0 adaptive technology continuously monitors variations in metal thickness and strength. Sensors communicate with the control system, automatically adjusting bending force to maintain uniform angles and consistent results. The seamless response of the machine reflects the harmony between design, material, and technology. Operators then program the machine for the kit layout, including bends of varying depth and sequence. The P4-2116 executes each bend with repeatable accuracy, even on heavy gauge panels that challenge conventional benders. The efficiency of producing multiple complex parts without manual recalibration emphasizes the importance of intelligent automation. Once bending is complete, components are visually inspected for conformity. Minor adjustments are noted, feeding back into the adaptive system for future runs. The combination of automated feedback and operator awareness ensures that each panel meets exacting standards. Finally, the completed kit is carefully removed and grouped for assembly. Each part is traceable to its original program, making post-production tracking straightforward. Seeing the finished panels aligned in perfect formation inspires appreciation for both machine capability and the human oversight guiding it. Every stage, though seemingly routine, carries a quiet intensity of control and dedication,